All right, let's talk about how to use dimensional analysis in order to figure out these conversions between grams and moles. So for number 37, what's the mass of 65 moles of sulfur? You always start by just writing what you've got, 65 moles of sulfur. If it's asking for mass, that means it wants grams. So how do you figure this out? The periodic table is really helpful because it tells you how much 1 mole weighs. 1 mole weighs 32.06 grams. And by the way, remember that 1 mole is 6.02 times 10 to the 23rd of something. So that's a lot of them. And that's equal to the average atomic mass. So that's what that is. So the 32.06 is how many grams per 1 mole of that type of atom. So 65 moles of sulfur, we know that 1 mole weighs 32.07 grams. We have a lot more than that. We have 65 moles. 65 times the 32 will tell us the total number of grams. And I rounded it to 2,100 grams of sulfur. And you can always cancel out your units, moles of sulfur, moles of sulfur, sulfur. Remember, things cancel out top and down diagonally, and then whatever you're left with on the top should be there so that you can write that for your answer. So if you can't remember, like, which way do I put it? Just remember that it has to be up and down diagonal to cancel out. Next one is similar, but it's just the opposite way. You're starting with grams. How many moles worth of sodium atoms do you have if you've got 435 grams? Well, 1 mole is about 23 grams, so you've got a lot more than 1 mole. You've got 435 divided by 23 about, so you've got almost 19 moles of sodium. Again, grams and grams cancels out and you're left with moles. 39 is kind of a weird question because it's just a precursor to, it was just practice for actually moving into atoms, but let's take a look at it anyways. What's the mass of 5 soda cans if 50 weigh 2,250 grams? Well, let's find out how much 1 can weighs. So 2,250 grams divided by 50 cans, each can weighs 45 grams. So if you have 5 cans, how much would they weigh? Multiply to get your answer. And then what if you had 20,524 grams worth of cans? How many cans is that? Well, since each can is 45 grams, you divide to figure out, okay, 456 cans. You could also set this one up with dimensional analysis to make it a little bit easier. You know that 45 grams is equal to 1 can, and so you can see you need to divide because grams will cancel out. Unit 2, this is a little bit more recent here. First question, will solid copper sulfate, and this should honestly have a Roman numeral here, that's a mistake. It should be like copper 2 sulfate so that you know how to crisscross, but it doesn't really matter because what we're interested in is this is a metal and non-metals, so we know that this is ionic. Okay, if you've got a big chunk of salt, is that going to be something that we want to make our pipes and wires out of? No, it does not conduct electricity. So we can really think about the material to help us identify the properties. If you dissolve a salt in water, though, then it does conduct electricity. Like my example, you don't want to be out swimming in a lightning storm in the ocean because that salt water will conduct electricity. And that's because when you put something like sodium and chlorine in water, it splits apart into these ions. So the reason it does that is because water molecules are so polar. Oops, I meant for that to be a partial negative, and these are partial positives. They literally pull that sodium away from the chlorine. And now it makes sense electricity can travel through something because electrons need these positive and negative charges in order to flow through. Explain how ionic bonds form. Because there's such a high difference in electronegativity, like between a chlorine and a sodium, the chlorine will actually completely steal sodium's electron. So there's a total transfer. Sodium is short one electron, leaving it with a full positive charge, because normally it has 11 protons and 11 electrons, but since it lost one, now the positive charges are winning by 1. So sodium gets this +1 charge, and chlorine normally has 17 protons and 17 electrons. Now it gets an extra electron, so the negatives are winning by 1. So now these two atoms are very attracted to each other with these opposite charges. What type of bonding would you expect there to be in the following molecules? A big hint when you see a gas is that it's molecular covalent. Okay, that's a sign. Molecular covalent things have low boiling points, so they can easily turn into a gas. This one has a metal and a nonmetal. We've been talking a lot about salt, so that gives it away that that's ionic. If it's a metal, then it's automatically metallic bonding, and if it's a liquid, it's another molecular covalent. Something that doesn't really do anything, doesn't dissolve, doesn't conduct electricity as a solid, and it's a hard solid, that sounds like network covalent. So an example of that in real life would be sand. And then the only one that conducts electricity as a solid is metallic bonding. All right, how do you figure out what charge an element will form? Well, one of the ways is you can look at the periodic table, because there are written, this is the cheat way to do it, there are charges written above the columns. And I'm not going to ask you about a transition metal because their charges vary. So for this question it says, what about potassium? What charge does potassium want to form? So let's think about the answer. Potassium's number 19. It really, really wants to be like the noble gas nearest to it, like argon. And the reason is, just as a little reminder, it's got 2 electrons, 8 electrons, 8 electrons, and then it's got 1 electron in its outer shell. If it gets rid of that 1 electron in its outer shell, now it will have 8 in its outer shell. So it'll be really happy. It'll still be potassium because it's got 19 protons in its nucleus, but it will have the same electron configuration as argon, 18 electrons. So that is why now that it has lost an electron, it still has 19 protons, but only 18 electrons, so the positives are winning by 1. So that's true for this other example of a metal too. Only magnesium needs to be like neon, and so it needs to lose 2 electrons. 12 minus 2 is 10. Something like bromine, though, it's easier for it to gain 1 electron, to be like krypton, than it is for it to lose its 7 outer shell electrons. So that explains the pattern for why those are forming negative charges, because they're actually getting extra electrons. Polyatomic ions are groups of atoms that all together have this overall charge. And there are 6 main ones that are definitely given to you on your equation sheet. So you've got those. Noble gas envy we've been talking about. Atoms want to have 8 electrons in their outer shell, just like the noble gases. So that's why they call it the envy. A cation is something with a positive charge, and an anion is something with a negative charge. So that's just really a question about those terms. When magnesium and bromine combine, they form MgBr2. Why? Well, magnesium's got 2 electrons in its outer shell, and it wants to get rid of both. But bromine has 7 in its outer shell, and so it really just wants 1 more. So 1 bromine atom is not enough. You need 2 of them to each take 1 of magnesium's outer shell electrons for them both to be stable. Transition metals have Roman numerals in their names because they can have different charges. Like on that other question I said I should have had copper 1 sulfate, or I could have had copper 2 sulfate, because copper can exist in some different forms and form these different charges. So the Roman numerals, 1 is just +1. Roman numeral 2 is just +2. Roman numeral 3 +3. And Roman numeral 4 +4. So those are the 4 that you need to know. List some elements that would be a perfect match for oxygen and form a 1-to-1 ratio, meaning not something where you have to crisscross the charges. So oxygen would really, really like to gain 2 electrons to be like neon. So you have to think, what group of elements would really all like to lose 2 electrons to be like a noble gas? So the entire 2A column, beryllium wants to be like helium. 4 minus 2 is 2. Magnesium, we already said, wants to be like neon. It wants to lose 2. So that entire group would like to lose 2, and oxygen would like to gain 2, so they're a perfect balanced match. Let's talk about crisscrossing. So number 50 starts with copper 2 chloride. So we've got copper, and that Roman numeral means +2. Chlorine has a -1. Ignore the charges and crisscross the numbers. So the 1 goes down, the 2 goes down, and then you never really need to write a 1, so it's just CuCl2. Lithium is a +1 charge. You can look that up on the periodic table. And nitrate is one of those special polyatomic ions. That entire thing has a -1 charge. If these add up to 0, they cancel out and you can just write the compound. Nickel with a +3 charge, and selenide, you have to look on the periodic table, find it, and say, okay, what column is it in? It wants to form a -2 charge. Okay. Ignore the charges and just crisscross the numbers. Ni2, Se3, that's your answer. Same thing here. Here's a Roman numeral 4. Nitrogen wants to form a -3 charge, so you crisscross those charges. Naming compounds is pretty simple as long as you remember to change the ending of the second atom to "ide." Unless, of course, it's a polyatomic ion that already has a special name. Drawing molecules. Start by drawing anything other than an H and try to make it symmetrical. So here I'm going to draw 5 dots because nitrogen is in group 5A. And the way that you normally draw them is start at the top, go around in a circle. Oops, 1, 2, 3, 4, 5, 6, 7, 8 dots. And since there aren't 8 for nitrogen, you would stop at the 5. So it ends up with 2 on the top. And again, the place where I get that is the group number. So nitrogen is in group 5A, so that means it gets 5 dots. So then you start figuring out, okay, let's connect them once, and I've got 2 hydrogens to put somewhere. So like I said, symmetry is good, so I'm going to put 1 on each side and connect those dots. And now I see there's still 2 lonely electrons I need to connect. Just for fun, the shape around this, because it's got 2 things attached and a lone pair on the central atom, this would be bent and this would be bent. Number 53, there's more than one way to draw C5H10O2. So here, let's just double check. Each of my carbons has 4 bonds because honk, 1, 2, 3, 4. So yay. My oxygens each have 1, 2 bonds. So that's checked off. And each hydrogen has 1 bond. So always double check yourself. That looks good. And we just talked about honk 1, 2, 3, 4. So that's the end of part 4.